In this video, we're going to talk about how and why we take a statistical approach to the fracture strength of ceramic materials. Let's start by considering the impact of defects on the strength of these materials. In a material like a ceramic, there is a statistical scatter in the defect sizes, and this leads to statistical scatter of the fracture data as well. So we may have cracks of different sizes or pores of different sizes which result from the processing of these materials. And this results in a much bigger scatter in the fracture data as compared to what we see in metals and polymers. As a result, we can't simply define a failure load for these materials, and instead we need to introduce a statistical fracture mechanics and give the failure probability. So let's take a look at how we do this. So we're going to assume that defects are distributed within a component and that crack propagation from one of these defects is ultimately what causes failure. And so what we're interested in is the probability of failure, which we're going to call P sub f, and we want to know the probability of failure as a function of the stress that's being applied. So this is the probability that a component will fail when a stress of sigma is applied. So as an example, if we knew that the probability of failure at 200 MPa was equal to 0.3, this simply means that 30% of components would have failed by this stress. So not that 30% fail exactly at this stress, but 30% will have failed by the time that we reach a stress of 200 MPa. And in this case, the failure strength is defined essentially as the stress at which the first crack starts to grow, and it will keep on growing. So let's look then at the mathematical distribution or expression which gives us this probability of failure. So here's the equation which tells us the probability of failure as a function of sigma. Let's just define the variables first. So we have 1 minus e to the negative sigma. So this is this same sigma is over here, so as a function of stress, which is divided by this variable sigma naught and raised to the power m. So in this equation, m and sigma naught are the fitting parameters. This distribution of failure strengths follows what's called the Whiteboard distribution, and m is what's known as the Whiteboard modulus. Let's take a look then at what this distribution looks like in terms of the probability of failure as a function of stress, and consider different values of m and sigma naught so that we can see what effect those have on changing the distribution. So here are two different examples, and I'm plotting the probability of failure as a function of stress, and we see the probability of failure goes from 0 up to 1. And I'm showing this for two different cases. In both cases, the Whiteboard modulus m is equal to 10, but the value of sigma naught is different. So let's just focus on this red line to start with. And so at stresses below about 200, there's no probability of failure. By the time that we get to a stress of maybe around 350 MPa, there's a 100% chance of failure. And this curve is a little bit steeper as compared to this one, but that's more just the fact that this has a lower value of sigma naught. So in keeping the same value of m, a higher value of sigma naught essentially shifts over the average value of failure for this material. So sigma naught is sort of telling us where is our curve centered, and as we'll see on the next slide, it's really the value of m that's telling us how steep is the distribution, or how narrow, rather, is the distribution. So here we're considering two cases again. This time they both have a sigma naught value of 300 MPa, but now the blue one has an m value of 5 and the red has an m value of 10. So we notice that they actually cross at the same point, 300, at this particular value here. But as m gets higher, the distribution becomes a little bit narrower. So the range of stresses over which failure might occur is smaller for a higher value of m. In fact, as m goes toward infinity, this would turn into just a step function. So let's consider how we would actually determine the values for m and sigma naught if we had a distribution of failure stresses as a result of some experiments that we had done. Let's start with our expression for the probability of failure as a function of stress. We're just going to rearrange this to begin with. In the next step, we want to get rid of the negative sign that's inside the exponent. For the next step, let's take the natural log of each side. On the right-hand side now, the expression that we have is a power law, and we know from experience that if we want to find the value of m, we should take the log of both sides. And finally, we can do a little bit of expansion of the right side. We now have an expression that's the form of a line. So this equals y. Here we have m, which is now the slope, times x, plus b, the intercept of the line. So if we have failure data where we know the value of sigma and we know the value of the probability of failure just from that distribution within the data, we can essentially plot the log of sigma versus this term over here and find the slope and then determine the intercept to get sigma naught. And in the video that follows this one, I will work through an example of how we actually do that. Let's look next, though, at the effect that volume has on the failure probability of ceramics. Let's imagine that we have a component that has this volume here, and we divide it up into two subvolumes that we'll call volume 1 and volume 2. And what we want to do is we want to know essentially what is the fate of volume 1 and volume 2. So will it fail or will it not? And so there are four possible combinations of the fates of these two volumes. So the first is that neither could fail, right? They could both hold up. The next is that volume 1 could hold up and volume 2 could fail. Volume 1 could fail, but volume 2 could hold up, or both of the volumes could fail. And what we want to know then is what is the total outcome? Right? So if either of the volume fails, the component fails. So while each of them had essentially a 50% failure rate or failure probability, we want to know what is the total failure probability. So in this first case, the component holds up. In the next, it fails because one of the two has failed. In the next, it fails. And in the last, it fails. So by virtue of looking at this with these subvolumes, we find that while each of them on their own has a 50% failure, in this case, there's instead a 75% failure. I'm not going to go through the full derivation here because it's in the textbook if you're interested in seeing. But we can essentially say that the probability of failure or the probability of success becomes the cumulative product of the probability of failure of each of the subvolumes. In the end, we end up modifying the equation for the probability of failure to look like this. So you'll notice the only difference now is that we have this volume term in here as compared to before, where V is the volume of the component and V naught is the reference volume. So that would be, the V naught was essentially the little volume on the previous slide. Now, if our problem doesn't tell us anything about the volume of the component or the reference volume, then we just leave that term out, essentially take it to be 1, and then we end up with the same equation that we had. So in summary, because of the statistical scatter in the types and sizes of defects in ceramic materials, we end up with having to use a statistical distribution to describe the failure of these materials. And we do so with this equation, which is also what's known as a Whiteboard distribution, or we could say that we are applying Whiteboard statistics to this problem. And in the next video, we will work through an example that shows how we find M, the Whiteboard modulus, and this reference stress sigma naught.